Stream up. And so, what do we got going on? We want to talk about oscillators and Laplace. WebAssign number 8 and worksheet number 8 are coming in today. WebAssign number 8 has 6 problems at the end, and those 6 problems are going to be a topic that we talk about today. They're not too bad. It's a nice transition into Laplace, so we'll talk about that. And then know that Laplace is going to stress our algebra a little bit, and so partial fraction decomposition and completing the square. I've posted some videos in the modules, so you can take a look at that. Okay. What do we want to do? I just want to wrap up the mass spring behaviors and stuff so that you can carry that on into other classes where you'll likely see phenomenon like that, and then switch gears into Laplace transforms where we talk about the integral definition and examples. Okay, so that's what's on deck. I'm gonna switch us over to the pad where we have the classic diagram of the mass spring system. Right? And what did we learn about last time? We said that if there is no drag in the system, then the system will want to oscillate indefinitely. If there is drag in the system or damping, it can be overdamped, which is pure exponential decay to the equilibrium state, underdamped, which is oscillations with decay to the equilibrium state, and then critically damped, which is exponential decay to the equilibrium state, and it actually happens to be the most efficient of pathways to the equilibrium state of no motion in the rest position. Okay, so this is what we've been talking about, and right now I would like to mention that this system is equivalent to the electrical oscillator, which is L standing for inductance times the second derivative of charge with respect to time times resistance times the first derivative of charge with respect to time plus 1 over capacitance times charge with respect to time, and that's equal to some sort of external voltage source that you could apply to the system. So capacitance acts like, or a capacitor acts like a linear restoring force like the spring. It stores up energy to release it all of the sudden. And then resistance is going to be trading the charge or the kinetic energy for heat. It's a heating up process, right? And then this piece right here is called the inductor. And the inductor's kind of kooky, and so to address the kookiness, I'd like to move us over to a video that's hanging out on our Canvas space, and then a nice animation of how we could think about a system that only has a capacitor or spring, analogously, and an inductor, or just a mass analogously, and we've gotten rid of drag or damping, and we've gotten rid of external forcing or resistance and the battery. So I'm going to switch us over to the pad, or not the pad, the Canvas site. And so if we go into, of course, where is it? This YouTube playlist right here, there's all sorts of media about masses and springs and stuff like that. And so what I'd like to do now is I'd like to have this person talk about inductance for us.
Welcome to my first video about inductors. So, what's an inductor? Generally speaking, an inductor is a device that temporarily stores energy in the form of a magnetic field. Inductors are usually just coils of wire, and one of the basic properties of electromagnetism is that when you have current flowing through a wire, you'll create a small magnetic field around it. So if you coil up a lot of wire, you'll get a stronger magnetic field. When current first starts to flow through the coil, a magnetic field starts to expand, then stabilizes, and then you've got some energy stored in the magnetic field. When current stops flowing, the magnetic field starts to collapse, and the magnetic energy gets turned back into electrical energy. So they're kind of like a temporary storage area for energy. You know how capacitors store energy in the form of a static charge and resist sudden changes in voltage? Well, inductors are very similar. They store energy in the form of a magnetic field and resist sudden changes in current. And if you only learn one thing from this video, remember, the current in an inductor cannot instantly change. It always lags by a certain amount of time.
Okay, so I'll let that stop and remind us that if we look at the diagrams again, there is this idea that the mass could keep moving to the point where the spring is elongated and pulling it back, but it has this energy stored because it's in motion, it's kinetic energy, and it's got to bleed all that off before it turns around and reverses course. Inductors have the same sort of behavior. It's just that they're kooky because we've stored energy in this field that we can't see or touch, but it's out there, and so we know that, and that's the analog. The inductor behaves like the inertial force from the mass spring system. So if we move down the list on the playlist, we'll find this video, and this video is of a capacitor right here in a circuit with an inductor. And so they'll show the magnetic field, though not talk about it in the same way exactly, not as in good detail. And we will see the particle, the electrons in motion on the circuit to give you some idea of what's going on here.
Connect the charged capacitor across an inductor, you will see a beautiful energy exchange take place between the two elements. These energy oscillations look as if the capacitor is saying, "You take the energy," and the inductor then says, "No, you take my energy." Why don't any of these elements store the energy and become settled? Let's have a look at the interesting physics behind these oscillations and some of the applications. Before diving into the LC circuit, we need to understand a simple circuit, a capacitor-resistor circuit. The capacitor is fully charged initially. Let's introduce a resistor into the circuit. Here you can observe that initially the current flow is at the maximum and then it sharply decays with time. This is expected because at the beginning, the charge difference is at the maximum, so the current has to be at the maximum. Now let's see what will happen if the resistor is replaced with an inductor. Here again, the capacitor is fully charged initially. It's quite logical to expect that there will be a huge current flow at the beginning, and then the current flow would reduce as in the previous case. However, this will not happen in practice. An inductor develops EMF across it, based on the change in current flow. This means that a drastic change in current is not possible across the inductor as in the previous case. Now the current flow starts from zero and increases to the maximum, and then comes back to zero again. In an inductor-capacitor circuit, the current flow variation has to be gradual, and here we can see that the current flow in the LC circuit is shaped like a sine curve. Let's look at the electron flow animation once again. The current in the circuit starts from zero and gradually achieves the maximum value. In the next 1/4 of a time period, the current from the capacitor starts to decrease, resulting in another change in current. At the end of the capacitor discharge, if you check the EMF across the inductor, it will have the opposite polarity to the initial EMF. This reverse EMF charges the capacitor with the opposite polarity. In the next half of the time period, the capacitor will be fully charged with the reverse polarity. This also means that the current flow will be in the reverse direction for the next half. Hence, in an ideal circuit, this back and forth flow of current would continue to charge and discharge the capacitor and form endless oscillations of energy.
All right. Okay, so those are the basic principles or pieces for circuitry, and what we want to notice is that they behave in the same way as the mass spring system, and we can expect that because the mathematical theory predicts that structurally they're the same equation, and so it's not unreasonable to see a correspondence between the two. Okay, so what we then were talking about was what's an interesting thing we could do if we were to externally act on the system, either with a battery or poking the mass spring system. And so one of the things that we looked at last time was this idea of resonance. Okay, so of most of the forcing functions that can exist, most are not very interesting because if they're exponentially or if they're growing in time, then the displacement would also grow in time because you're supplying more energy over time, right? Or if they're decaying, the external force is decaying in time, then it'll just be the homogeneous solution. What we have for resonance are the following key ingredients. The first key ingredient is that we have this thing right here, which is my external forcing agent, which is a periodic forcing function in time. Okay. Now this mass spring system is going to have a homogeneous oscillation like the LC circuit that we just saw, and that would make a sinusoid, and that sinusoid has a particular frequency. So the game for resonance is to take the external forcing function and supply it with a period, or give it a periodic nature and give it a frequency that is exactly the same as the frequency with which the oscillator wants to oscillate in time. What that means for us is the particular solution is the same as the homogeneous, so the particular solution picks up a T multiplier. And if we track this problem all the way through, what we see is that right here, we pick up that T multiplier in the particular solution. And so what we see is that there's a sinusoidal oscillation, but the amplitude for that sinusoidal oscillation is growing in time. And so what that growth means is that there will be lines coming out of the origin like this and like this. And those lines will allow for a growing amplitude of oscillation, and that growth in amplitude is resonance. The external force is at a frequency which the homogeneous solution wants to accept. There's constructive interference of waves at all times, and that grows the energy in the system, and it can be seen with amplitude increase. Okay? And so, what is that amplitude increase? Well, we've shown with this Tibetan singing bowl, if I send it into motion, there is my oscillation. And then I can supply an external force in a periodic way to get it to be louder by increasing the amplitudes of oscillation. Jenna in chat is asking, can we have resonance when B is equal to 0, B being the coefficient of the drag force? We can, but the analysis gets a lot tougher to see through because there are two key components. The energy coming in from the external force and the rate at which the energy is being lost due to drag or damping. And so now we have to be critical of how quickly we're bringing it in versus how it's losing. So right here, right, if I just don't help this thing out enough, right, then I'm not supplying it with enough energy to counteract the drag or the damping that's already going on in system. And so, so there's just an interplay there. Good question. Cool. So then, how does this look for LRC circuits or LC circuits? Well, we saw how it looked for the tuning forks, right? We were able to energize this other tuning fork setup when this mass was removed by sending out acoustic waves at the right frequency to energize this. Well, the same thing is happening in a Tesla coil where there's a first component that kind of starts the oscillation going and starts powering up charge to the second component, and charge gathers to the point where it will arc off of the top and produce a sound, not the greatest sound in the world, but it will produce a sound. And so that is what's going on behind the scenes in a Tesla coil. Okay. Okay, you might wonder where the sound is coming from, and it's because the arc that comes out, the radius of that arc is expanding and contracting. That's what makes the acoustic vibration. Then the last thing I would like to talk about is if resonance can be utilized, that's good, but a lot of times resonance needs to be abated because if amplitudes grow without bound in time, you might hit a displacement for which the structure or the system cannot tolerate. And once that happens, some sort of structural failure will occur, and that would be a bad thing, especially if it were like on a bridge or something, right? And so if resonance occurs when the frequency of forcing is precisely equal to the natural frequency of oscillation, you could ask what happens when they are not equal but close, right? And so what would you do mathematically there? You just go back to the same differential equation, solve it again. You won't pick up a T multiplier, and what can be found is a set of cosine functions in this case, but to see what happens, we have to apply this trig identity. I'm not going to do that. I'll just tell you about it. And then what I want to notice is that after application of the trig identity, you can get to, and these will all be in the notes, the product of two sine functions. And so let me, in green right here, highlight this sine function and say, okay, this green sine function. Okay, I know I got two sine functions here, right? And that's kind of a lot. Well, I'm going to forget about this rightmost sine function, and I'm just going to think about this green function and forget about all this stuff out front. That's just a number. I'm looking at the green box. Well, the green box multiplies the sine function. So the green box changes the amplitude of this sine function. If omega is close to omega naught, let's say omega is 1 and omega naught is like 0.99, then 1 minus 0.99 is going to be pretty close to 0. So the indicative quality of this green box right here is that this is an oscillation which is slow in time. Omega minus omega naught is approximately 0. So that makes this outer oscillation slow. But that's not the whole story of the function, right? The outer oscillation is slow, but this oscillation is going to be much faster because if omega is 1 and omega naught is 0.99, then if I add them, you know, I'll get something that's not very close to 0. And so what happens is I have a sine function right here, which makes a wave, but the amplitude of that sine function is modulated so that that modulation is slow. And what we see occurring is because of the constructive and destructive interference of the waves, an envelope forms, and that envelope is a slow oscillation. And then inside that slow oscillation is the actual solution to the problem, which is y of t. And that y of t oscillates at a frequency that's much faster, but what we see is that the amplitude of this inner oscillation, which is the solution, varies in amplitude over time. And so what you would witness in the mass spring system is a little bit of jiggling, growing to bigger displacements, abating to little displacements, and then that process repeats itself. And that's what's called a beat. So if resonance is when the frequency of forcing is precisely equal to the frequency of oscillation, beating is a precursor to resonance, and beating can be noticed because the amplitude of oscillation increases in time and then decreases, and that there's a pattern of that increase and decrease. What might this sound like if we were listening to it? Well, we go back to the tuning fork demonstration. And so that graph that you were just looking at is the graph which corresponds to the sound which you're about to hear. The sound is caused by oscillations of the amplitude envelope and so this wubba 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 sound is that oscillating beat pattern, and that's what we're hearing. Okay. So I see a question in chat. So if they asked for amplitude, you would just say it's changing? I think if you're talking about the worksheet, there's a problem in the worksheet that's asking you to find the amplitude of the homogeneous solution. So you'll have to pick that one out of the two trig functions that are there. Okay. So that is the gloriousness of vibrations as they appear in the form of differential equations in the two most prominent models of LRC circuits and mass spring systems. We need to understand the role of damping, and then we need to understand of the external forces, which are the interesting ones and why are they interesting. Those are the key points to come away with. Okay. With that said, I will close down the talk of mass spring systems with the exception of one more auditory example, and then change gears to Laplace. Amplitude is the number in front of the sine function, right? Yeah, totally. Yep. And in the beating case, that's changing. It's oscillating in time slowly. And in the resonant case, it's just growing in time. Okay. So we have this singing bowl that we've looked at. And with this singing bowl, it has a frequency of oscillation. I can resonate it. But what we don't have currently in the model, even though this isn't exactly a mass spring system, there are analogs here, we have no analog for this. What is this? This is an external force. It gives energy to the system, and since I strike it, the energy goes into the system very quickly, and then the force backs away and doesn't do anything, and then the system just lives with that energy. Okay, so Mach is not good enough here. We will not make forward progress with Mach, and for these problems, we have to introduce a whole new type of mathematical tool, and that mathematical tool is called the Laplace transform. Okay, so this is the initial slide for the Laplace transform, which I'll talk about quickly and then just get with examples. But what you want to do right now, I'll point you in the direction. You want to look for a PDF that has this sort of table structure to it. And I will show you where you can find that PDF. If you go into our listing of videos, you'll find right here, and it's also in the modules, that there is a PDF for this Laplace transform table. And so you're going to want to pull that down, keep it in a tidy location. If you want, through the coming lectures, print it out and take notes on it. That would be ideal, because what we're going to do now is we're going to develop a new mathematical tool that will eventually allow us to have that pulse of force, or if you were a circuit, like a surge of current. Okay. All right, so that's the motivation. Oftentimes, we would like to pulse mechanical and electrical oscillators with a finite amount of energy over a very short duration in time. And this, as you might expect, would lead to sudden changes in the output behavior, right? The singing bowl does nothing, and then I pulse it, and then it sings for me, right? And then I can make it sing more with resonance, but I'll still hear it after the pulse, the strike, right? Mach will not work for this, and so we need a new tool. Here's the tool. Let y of t be a function of exponential order. Let's not worry about that right now. Let's just proceed formally and see how this works. Then the following exists and defines the Laplace transform of y. Laplace is the name of a person, so it's capitalized. The transform is going to be illustrated now. Okay. I am going to... Okay, there are various ways to write this, but I'll show you mine. I'm going to make the most fantastic cursive L that I can. It will have curly brackets, and it will accept the y function. If you're not with that sort of froofiness associated with the writing, I taught C++ at a board for many years, so my curly braces, I've put a lot of work in there. And then the L, I've taught Laplace transforms once or twice in my day. Right? But if all that's too much, then just write L bracket y, just go for more 90-degree angles. And so what is this thing? This thing, whatever comes out of this, I'm going to call capital Y of S. Okay? And what is capital Y of S? It is the integral from 0 to infinity of y of t e to the minus s times t dt. This is the thing. Why is this the thing? Well, this Laplace transform, since it is an integral, if there's some sort of pulse behavior, something for a short time duration, then this is going to be pretty tolerant of a function that's like do nothing, do nothing, do nothing, strike the thing with the hammer, do nothing, do nothing, do nothing, right? It's not constrained to the algebra of Mach. This integral will be tolerant of that sort of spiky behavior within the force description, okay? So, why is it called a transform? We'll check it out. This is an integral, a definite integral with bounds from 0 to infinity. The integration variable is t, so when I put in upper and lower bounds, there won't be any t's anymore. And then what will be left is a new variable that's introduced called the s variable. I'll call that the Laplace variable for now. And so when the function is represented in the t variable or the time domain, I'll give it a lowercase y. And then when it's done being transformed by this spectacular coordinate transformation defined by an integral, the new variable is capital Y, the new dependent variable, and then the new independent variable is little s. Okay? Yeah. Be careful with your 5s, right? The worst problems that I can write are problems that have the number 5 repeatedly in it, because your 5s are going to start looking like s's. And so what you're going to want to do with your 5s is you're going to want to really work hard at this 90-degree elbow right there so that you can keep them separate. Okay. And I mean, I just made the top wavy because my hand was shaking. Don't do that. All right. In the long run, we're going to work through a table. The table will be like our Rosetta Stone. Let's look at the table for a second. The table is saying, hey, you got a function f of t? Well, say that's e to the at. If you were to shove that function in the integral and do work on it, you would get a new function in the s variable, and that function would be 1 over s minus a. This is like e to the at, but in disguise in the Laplace side after it's been transformed. Okay? So what we want to do right now is just to get a feel for the integral transform and the table, and then ultimately we're going to build up to using a new function to thwack things. Do we get the Laplace table on exams? Yes, you do, and it will not count to your 1 page of handwritten notes. Yeah, you'll need this. This will be, yeah, this is a requisite. Okay, but let's get a handle on the integral first. For instance, let's say I have this. I want to take the Laplace transform of this f of t. And this f of t is like not a lot of other f of t's that we've looked at so far, because this f of t is 0 for the first 6 seconds, let's say, and then the number 1 for all seconds after that 6th second. So when we did muck, we didn't look at a function that was like, yo, I'm one function and then I become another function for the rest of time. We didn't look at jump discontinuities. But since this is an integral, it will handle the jump discontinuity just fine. Why would it handle the jump discontinuity? I'm going to take the Laplace transform of this thing. When I do, I'll get a new function, capital F of s. And how will that function be defined? It will be defined as the integral from 0 to infinity of f of t e to the negative st dt. And then what do I notice about this function? I notice that there is a change in behavior at the 6-second mark. But integrals are okay with that, because the integral is going to say, okay, if there are going to be 2 types of functions, the function 0, then the function 1, why don't I break my integral up into 2 different domains? One domain from 0 to 6 seconds, and then another domain for 6 seconds all through the rest of time. So the integral, which is the Laplace transform, sees that, and it's like, it's fine, I'll just break myself up and I'll treat it as 2 parts. Okay? Well, as these 2 parts, for the first 6 seconds, I'm on this integral right here, but what is the f function for the first 6 seconds? Well, the f function is just 0 for the first 6 seconds, so this f function right here is 0. But then what is the f function for the seconds 6 and beyond? Well, let's give that a different color. I'll give it a color purple here. And then what is that function? That function is just the number 1. So what does this become? This becomes the integral from 6, let me just write it up here, the integral from 6 to infinity of e to the negative st dt. So now I anti-differentiate e to the negative st. I remember I'm anti-differentiating on t. So I anti-differentiate e to get negative e to the negative st over s from t equals 0 to t equal infinity. Okay, quite formally, I'll interject for a second, quite formally, this would actually be the limit as capital A goes to infinity of some stuff written above from t equals 0 to t equal capital A. Okay. Oh, t equals 6 to infinity. Thank you. Like that. Okay. But it's common at this point, despite your Calc 2 training, that you just treat infinity like a number and avoid the usage of limits. Why is that okay? Well, it's not really. But why is it okay for us? Well, at the end of the day, we're going to be working off the table. And working off the table, we're going to forego some of the formalities that are in here because we're looking to just move the problem forward and not get stuck in the mathematical weeds underneath. Okay? So that is my statement about the abomination that I'm about to write down by treating infinity as a number. But I'm going to do it. I'm in a basement. None of you can stop me. So I have e to the negative s times infinity over s minus negative e to the negative s times 6 over s. And now here's the game. This is an exponential function. As you start putting in infinite limits for the argument, this function may either blow up and diverge, or it'll converge to the number 0. For this Laplace transform to work, we need to temper this possible divergence, right? And so, I know it does look so wrong, doesn't it? It pains me. It pains me too. And so I'm going to keep an eye on this s right here for the next equality. What am I going to prescribe for that s? I'm going to say that that s is greater than 0. Because if that s is greater than 0, I'm going to e to the negative infinity, right? And e to the negative infinity, what is that going to result in? That's going to result in a 0. And then I get a negative times a negative, which is a positive. Then I get an e to the negative 6s over s, and that's the result. E to the negative 6s over s, where s is greater than 0. This thing right here, this is my capital F of s. It is the piecewise function written in disguise in the Laplace space defined by the s variable. Cool. Questions? Does the table do all these steps for us? The idea with the table is that if we can honor the fact that it comes from an integral, then if we put the same function into the integral, then the result, we don't need to reintegrate every time. It'll just keep coming out with the same output. So the table is a record of somebody else having done all the integrals, found the patterns for us. We're going to do a few to practice so that we know where it comes from. But after that, the table is a record of the hides the intermediary steps and is a record of the output. Okay. Sean's saying this doesn't seem too bad. It's not. It's really not. But it will get cumbersome at some point, and it'll stress our ability to keep the books. No one part will be hard, but the bookkeeping ledger will be onerous at points. Okay. So I will freeze. I will set up the next slide, and we'll transfer over in 3, 2, and 1. I'm going to check out that chat question in a second. I'm going to put up the 2-minute timer. We have time. And so why doesn't everybody try to do this through the integral? And I'll write the integral down here. It's an integral from 0 to infinity of f of t e to the minus st dt. So everyone should give that a twirl in the 2 minutes, and I'm checking in on chat. All right, coming back here. If I'm asked to take the Laplace transform through the integral definition, then what I'm being asked to do is to take the function, plug it into the integral, and start bringing out your integral trick bag. Here, the function is e to the 3t plus 1. So for f of t, I plugged in e to the 3t plus 1. What do I want to notice about e to the 3t plus 1? Well, that can factor into e to the 1 through exponential rules times e to the 3t. Now this e to the 1, it doesn't have any t's in it anymore, so it's a number. And that number doesn't care if it's setting inside the integral or out, so I pull it out. So now I have e times the integral from 0 to infinity of e to the t times e to the negative st dt. And so what am I going to do? The bases are the same, so now I'm going to rejoin. Oh, yeah, it's a 3t in there. Thank you very much. I dropped a 3 on my first exponential. People are noticing. Thanks, thanks. And now that the bases are the same, I'll add the exponents. And so tell me, what goes inside this parenthesis? Yep, a 3 minus s. So now what do? I integrate with respect to t, and when I integrate with respect to t, this 3 minus s does not care. So what do I get? I get an e from before times a 1 over 3 minus s times an e to the 3 minus s times t. Evaluate from t equal to 0 up to t equal infinity. Okay, now I'll write out the horrible notation, e times 1 over 3 minus s times e to the 3 minus s, all of this actually is times e to the 3 minus s times infinity, minus e to the 3 minus s times 0. Can f of t be a quadratic function? I'm going to do a linear example next. Cool. And so what is this e to the 0? This e to the 0 right here, that's just a 1. And then what do I want this term to be? Well, I don't want it to blow up. And so this first term, I'm going to say that 3 minus s, you better be less than 0. So that means that s has to be greater than 3. And if s is greater than 3, then this goes to 0. And so what do I get? I get an e times a 1 over 3 minus s times 0 minus 1. And so I'll take this negative 1, I'll multiply it into the denominator to get an e times a 1 over s minus 3, where s has to be greater than 3. Okay, that's the game. I'm going to freeze that, grab the next slide. Coming back over. Why did I multiply the denominator specifically? That's a good question. I just didn't want the extra negative hanging around. It's probably better in terms of habit to keep a negative out of the denominator and just scoot it into the, or out of the numerator and scoot it into the denominator instead, so that odds are I don't drop it. But there's nothing wrong with leaving it up top. And then it's asked in chat, do we always set up the s so that the term that could diverge actually goes to 0? And yes, you do. Okay. Switching over slides in 3, 2, and 1. Here, f of t is equal to t e to the negative t. So what does that mean that I got to do? Well, first I'll come back. I got to find f of s. What is f of s? F of s is the Laplace transform of little f of t. What is the Laplace transform? It's the integral from 0 to infinity of t e to the negative t times e to the negative st dt. In other words, the integral from 0 to infinity of t, the bases are the same, so join the exponents. In the exponent, I will pick up, let's see, A negative t factors out, so I will get a negative 1 minus an s in my exponent. And now I've got to integrate. How am I going to integrate this? Well, I see a t multiplying that exponential, so this is a by parts problem. For my u, I will choose t. I take a derivative to get 1. I take another derivative to get 0. For my dv, I have e to the negative 1 plus s quantity times t to just tidy that up a little bit. I anti-differentiate to get e to the negative 1 negative times 1 plus s times t over negative 1 plus s. And then I get an e to the negative 1 plus s times t all over 1 plus s quantity squared. I go down and to the right with a plus. I go down and to the right with a minus. So this is equal to negative t e to the negative 1 plus s times t all over negative positive. I've brought that negative into the numerator, 1 plus s. Evaluate at t equals 0 to infinity. And then I get negative e to the negative 1 plus s times t all over 1 plus s quantity squared. Evaluate from t equals 0 to t equal infinity. Okay, as Sean was pointing out in chat, when you let t go to the upper bound of infinity, you're going to choose an s so that this is e to the negative infinity and it goes to 0. So at this upper bound, the two things that can happen are divergence or decaying to 0. I want decaying to 0. So I'm going to set up my s for that. I'm not going to record that on the regular. The table takes care of that in the long run. But at the upper bound, I get 0 because of the decaying exponential. When t is equal to 0 at the lower bound, that t will be 0. So I get 0 at the upper and lower bounds. And then here I get negative times, at the upper bound, when t jets off to infinity, I need this to be a decaying exponential, so it decays away to 0. And then when t is equal to 0, that t is equal to 0, so I get e to the 0, which is 1. So I get minus 1 over 1 plus s quantity squared. Then negating all my terms, in disguise, this function looks like 1 over s plus 1 quantity squared. All right. So I'm going to freeze there. Fade out. Get the next situation up and running. And then grab our helpful tool. Okay. And I'm going to switch over to, does s need to be greater than negative 1? Yeah. Yeah, Rebecca's asking, can we ignore the infinity times infinity, right? That's a great question. And that infinity times infinity, if we wanted to be formal, which is not our long-term goal, that would be resolved with L'Hopital's rule. You could show that if you wrote out the limit, then the limit would be dealt with L'Hopital's rule, and you'd still get 0 at the end. Okay. All right, so switching over in 3, 2, and 1. Okay, I've got my table at the ready. It's going to be over the top of me now, so I've got a table up here instead of my face. And so let's calculate the Laplace transform of this function right here using a table. First thing, what is the Laplace transform? The Laplace transform is an integral. How is the integral going to treat all of these things that are added together? Well, it's going to pick them off a piece at a time. So if I take the Laplace transform of little f of t, that means take the Laplace transform of t squared. Add that to the Laplace transform of 3t. Add that to the Laplace transform of negative 4. So what do? I go into my table. I search my f of t column for something that looks like t squared. Okay, here I have t to the n, but my n would be equal to 2. So if my n's equal to 2, like t squared, what should my output be if I were to do the integral? It should be 2 factorial over s to the 2 plus 1. So this first term, which is the Laplace transform of t squared, is going to be, hold on, got to get my pen synced up again. It's going to be 2, oh man. All right, for those that are watching, write 2 factorial over, okay, I've got to come back in real quick. Okay, well, we're going to have to do it in the following way. My pen has decided to dissociate from my pad, and so, where are we at? I will just point them out. Does it leave a factorial, or do you just calculate it? You can just calculate it if you want, or you can leave it in factorial form. So this t squared will become 2 factorial over s to the 2 plus 1, so that's 2 factorial over s cubed. So I'll write that in chat. That would be the first term. I feel weird not being able to write anything. Next, 3 times t. Well, what is the Laplace transform? The Laplace transform is an integral. Does this number 3 care if it's inside the integral or outside the integral? It doesn't care. So the 3 would factor out, and then you'd just be left with the Laplace transform of t. But then what is the Laplace transform of t? The Laplace transform of t is 1 over s squared. So this term, the Laplace transform of 3t, would just be 3 divided by s squared. Are these each individual integral or the big one? It's the big one, but remember the integral of a bunch of things that are added together would just be the individual integrals. Then you take the Laplace transform of -4. Well, the -4 doesn't care if it's inside the integral or out, so that's basically the same as taking the Laplace transform of the number 1. So this third term would transform into 1 over s, but then times that 4 that was out front. Okay. What are we going to do with t plus 1 cubed? I'm looking right here. These are all my power functions, and I don't see anything that's like t plus 1 cubed. So what am I going to do? I'm going to just FOIL that t plus 1 cubed all the way out into each of its terms. I know how to take the Laplace transform of the number 1. I just did. Well, actually, the number -4. I know how to take the Laplace transform of 3t, because I just did. I know how to do a squared, and then I just use the formula again for cubed. Okay? So it breaks off a piece at a time, and now we're only left with the Laplace transform of -4 sine 2t. So again, I search the table. Those look funky. Hopefully we deal with those at some point. Oh, exponentials times sines and cosines, that's close. Oh, there's my sine function. For this sine function right here, what is my k value? 2. So when I take the transform, what's it going to be? It's going to be 2 over s squared plus 2 squared. And then don't forget the -4 that's out front. So that is the integral and how the integral works. But then what are we going to do? We're going to default to using the table because those integrals have patterns that have already been done. And so when you're looking at the table, you just got to find your function and break the sum off a piece at a time. Okay. So once I get my pen associated, I'll write down the result of this Laplace transform through the table. I'll mark where the table elements were. I'll upload that to the drive. And then other than that, have a great weekend and a good day. For WebAssign, can we just table it? There are a couple problems that ask you to set up and do the integrals. Yep. It's not bad. Just refer back to these notes. All right, and it's being asked in chat, what is S? That is a trickier question. Next week, I'll put up a video that will kind of help, but there's not a good intuitive understanding of S without bringing in other contexts. But it's a great question, and that video will help out a little bit. Cool.
I just have a quick question.
Yeah, what's up, Jenna?
The end of the problem, I think.
Which problem?
Like the one that we just did.
Yeah.
The Laplace transform, like the final solution, would be just doing all of those integrals and plugging each of them at the right bounds, or maybe this one doesn't have bounds actually.
Well, if you're talking about this last one, then
Yeah.
by using the table, you get to avoid the integral. You don't have to do it both ways. And so this says, since it says using the table calculate, you go to the table, you see what the result would have been had you actually performed the integral,